Hey, this is Yash. This is my AE 1601 glider report. So the overview of this project is to design, build, and flight test a glider made from the materials given to us and ones that can be easily accessible. The overall goals of this project is to create a glider that is not only stable during flight, as in it minimizes roll and yaw, but can fly at least 20 feet straight. And also in the process, we get to learn more about the engineering design process and the ins and outs of that. So our given materials was a half inch by half inch by 24-inch square dowel and a 3 by 24-inch sheet, both made of balsa wood. Now there are some constraints and restrictions as well. It had to fit within a 16 by 16-inch box, meaning it's a pretty small glider. It's hand thrown and gliders no propulsion system, as seen on the right. And this last one is not necessarily a constraint or restriction, but to a good glider should remain intact during takeoff and landing. There are three major design choices. Part one is your wing shape with three types. So there's rectangular, which is easy to make and less likely to stall. However, it's a high amount of induced drag compared to the two other design choices because of its more surface area. Type two is a tapered wing. It's easy to make and less induced drag than a rectangular wing because the root chord is longer than the tip chord. However, it is susceptible to stall, so it's important to think about angle and tack when throwing it. Type 3 is your elliptical wing. Its induced drag is least of the three, as lift is basically zero at the tip chord. However, it is difficult to make and perfect, so it would require me to use a laser cutter to perfectly get the elliptical shape. And the angle attack is crucial since it can also stall pretty easily. Part 2 is a wing dihedral. There are two options. Either it has dihedral or it doesn't have dihedral. If it has dihedral, it's more laterally stable, meaning the roll is not a major factor in flight, so you get more straight distance. However, there's an increased amount of lift induced drag because the lift force is acting both horizontally and vertically because at an angle, and it's also not easy to build. With no dihedral, it's easy and simple to construct, but there really is no stability benefit. For tail configuration, there are two types, T-tail and conventional. T-tail is good pitch control and glide ratio, so it's more efficient on low-speed aircraft. So this is being launched by my hand. It's a low-speed aircraft. And the cons, it's likely to enter a deep stall. Conventional, it's more stable and used by most conventional aircraft, and it's more likely to experience more of a general stall, like a deep stall. Now, my initial design. So materials, decided to use a balsa wood fuselage and cardboard wings in the tail. It's only a prototype, so I wanted to test with cardboard first. The wing is like a mix of a rectangular and taper, with a taper beginning halfway between the root and tip chord. It was a perfect middle ground, in my opinion, between the benefits and difficulty of building. For dihedral, I chose to have no dihedral. I want to test out both in future prototypes, but to start, I decided no dihedral. And tail configuration, like dihedral, I want to test out both types, T-tail and conventional, but the T-tail seem more appealing. The pros of T-tail seem more appealing for me. So for sizing and sketches, I thought the fuselage should be about well, not me, but the research said that the fuselage should be about 3/4 the length of a wingspan. So in this case, it's 9 inches for the fuselage and 12 inches for the wingspan. The leading edge of the wing should be faced about a third from the front of the fuselage. An aspect ratio of approximately 6 is ideal, with a taper ratio of 0.5, which you can see here with the root chord being 1 inch and tip chord being 0.5 inches. And the wing's horizontal stabilizer and vertical stabilizer are all tapered. Now you can see a prototype 1 here. 3 total test flights, all of them similar result to that. So the glider takes an immediate nosedive after flight, so it showed that a new design was necessary. Now for iteration 1. I decided to switch to all cardboard, and I decided to increase the wingspan length to 16 inches and fuselage to 12 inches because I wanted more lift, so more surface area. However, I need to keep the 3/4 ratio. The wings now have full tapers of a half taper, and the T-tail is now switched to a conventional. Here's what the prototype 2 looked like, and based on testing, it hit the 20 feet benchmark pretty easily if I threw it correctly. This is my best test flight right here. It's about 31 feet, and what I learned is that the sizing and design choices were the ones that I desired. So this is my iteration 2, so my final design. Basically, it's the same thing except I built it out of all balsa wood, and this ended up being my final glider. I had 3 total test flights, and my best one went 45 feet, as seen in the video on the right. And the final design also has a slight dihedral, about 3 to 4 degrees, and stayed intact during flight. So I thought it was a successful test. The center of gravity is glider, so a good center of gravity should be located at the quarter chord to ensure stability. My center of gravity was located approximately at the quarter chord, if not a little bit behind, so it was still relatively stable. However, in future designs, I could probably fix it to bring it more towards the nose. To calculate the lift coefficient of this glider, I needed to weigh it, find the average velocity, and find the wing planform area of one end of one side of the wing. And I found lift coefficient to be 0.17. The drag coefficient, I had to take the lift coefficient from last slide and divide it by pi times E, which is the Oswald efficiency factor, times aspect ratio. And I came up with the induced drag coefficient about 6.1 times 10 to the negative 4. The total drag coefficient is basically 2 times the lift induced drag coefficient, because the zero lift drag is the same based on assumption. So we got 1.2 times 10 to the negative 3. Now for the actual fly off. This is the video taken on test day. So revisiting design requirements. Did the glider fly at least 20 feet? Yes, that glider flew 31 feet on test day, which so cleared the water of the benchmark. The size of the glider was within a 16 by 16 inch span. The wingspan was cutting it, but I think I maximized efficiency with the size of the wingspan because and the fact that fuselage length was only 12. The glider stayed intact during flight and was also made out of primarily balsa wood, along with some Benzier, which was allowed. Now for some conclusion and final thoughts. I think this project was a culmination of what we learned in our AE 1601 class throughout the semester, with earlier lectures like lift and drag, aerodynamics, stability, airfoils, and also one of the most important lectures about the engineering design process, as based on that diagram below, which will be a focal point of the work we do here at Georgia Tech and our futures, whether it's research or internship or job. You have to understand the requirements of what you're being asked to do, then go through some design alternatives, test it out. You're most likely going to have iterations in your design, and conclude from there. In terms of areas of improvement, I think with this project, given the time, I focus more on stability and hitting that 20-foot benchmark instead of going more above and beyond. So I think for next time, I want to focus more on maximizing my distance. So I would change my wing shape to elliptical and combine that with a T-tail configuration, like seen in this glider here. I think with less amount left induced drag, I would get a distance about 50 feet maybe on my best test flight or higher. Here are my references, and that's the end of the video. Thank you so much for watching.